Okay, thank you for coming. I'm very glad to be here today. Actually, I'm a little flattered. As told before, I was a backup speaker, so I didn't really expect to give you this presentation until last night. They told me that I can talk in this track. So my presentation is mainly about an exploitation method that can be applied for use of freeze in Adobe Flash. And before we start, here's a brief introduction of myself. I'm a security researcher of Pangu, and most of the time focusing on Flash security, find its vulnerabilities, and keep track of the state of art of exploitation. And many of the bugs I report to Adobe through the Internet Bug Bounty. And right now, I'm the top 1 contributor of this Internet Bug Bounty, but it has stopped recently. So the Internet Bug Bounty doesn't accept Flash vulnerabilities anymore. The method I'm going to talk about today is developed during the research of CV 2016-1097, which is a use of the free I found and reported to Adobe this May. So this is the agenda of my speech. I will start by introducing the basic ideas of how Flash exploit works and how recently mitigations prevent the classical trick. Next, I will show you my method to bypass these mitigations. And then we will build exploit step by step with this method for CV 2016-107. At the end of the talk, I will discuss how to exploit in the 64-bit environment and how Windows 10 affects the exploitation. So for the past 3 years, Flash exploit, no matter what type the bug is mainly about corrupt the length field of a vector object. So for example, heap overflow. The exploit will start by spraying vectors in the memories and leak memory holes. So free some of the vectors, and the vulnerable buffer will occupy one of these memory holes and then corrupt the length field of the vector object by triggering the overflow or the out-of-bound write. So the vector with a very large length will be used to search the process memory for rope guardians, shellcodes, buffers, and all kinds of structures you might need for the exploit to work. And finally, the rope chain will be executed by perhaps a fake virtual function table. And when it comes to use of the free, the process is very similar. With a proper heap memory layout, the vulnerable object falling in one of the memory holes will be released because of use of the free, then occupied with controlled vector data. Now, after the member function of the stunning pointer is invoked, fully controllable memory write will corrupt one of the length field of the vector object. And when we find that a corrupted vector, everything else goes like the same of heap overflow. So the length field is located at the beginning part of the vector object. It is very convenient to be cropped with a virus of Flash, even browser vulnerabilities. So this technique has been used maybe 3 or 4 years, almost dominates all of the Flash exploit in the wild. And normally, Adobe only fixed the bug itself instead of exploitation method. So it's very popular, and until last December, if I remember correct, it is because the hacking team's Flash exploit that is so popular, Adobe finally decides to working with Google Project Zero and adds mitigations to vector object. So after the mitigation, the length field is moved to the metadata part of the vector object and left with only a verification cookie staying in this old position. Now, since the length field and the cookie are now staying in different memory blocks, corrupted at the same time is not practiced anymore. So the cookie is the verification of the length field. It is calculated where a security value, it is calculated with a security value XOR the length. So if you corrupt one of these fields and the collision with the security value, it won't work for the memory write or read. And besides the vector mitigation, maybe just a month later, Adobe also adds verification fields to ByteArray, which is another very popular array-like structure inside Flash. Since the vector doesn't work anymore, so people try to exploit vulnerabilities with ByteArray, but not before long, maybe just a month later, verification fields are adding to ByteArray. But while the length field and the verification are now still staying in the same memory block. Although very rare, powerful zero-day exploit, including those used by Pong2On, were able to read the verification field first and then calculate the security value by XOR the length and the verification field, and then corrupt the length and the verification field at the same time. But this behavior is highly depends on the quality of the vulnerability. So to read and then corrupt means this bug itself, let's say a type confusion, should be capable of read and write any piece of the memory. So besides the length mitigation, isolated heap is also introduced into Flash. So right now there are many heap partitions inside Adobe Flash. And this mechanism has been first explained in Google Project Zero's blog. And basically, the data and the object are now separating into different memory blocks. So even if there's a use of the free of the ActionScript objects, we're not able to occupy the memory with ByteArray or vector anymore. Yet it is still possible to control and occupy the memory of this freed object with other class objects in the same heap partition. And that is something we're going to use in my exploit. So in conclusion, for the mitigation part, it has disarmed the classical and popular Flash exploit. And before the mitigation, there may be 2 or 3 Flash exploits in the wild for months, but after the mitigation, there may be just 1 or 2 for half a year. So the mitigation itself is very useful and powerful. But today, we mainly focus on use of the free. Let's see how to bring it to life. So what is necessary for use of the free to work? I think read primitive helps a lot, and that is the past 3 years Flash exploit or shares. As there is memory randomization, only with the read primitive can you find all the rope guardians and wrappers code and all the buffers you need. And as we're talking about the use of the free, we're able to fake the virtual function table with just memory occupation. So a memory write is not a necessity. Currently, exploit gain read primitive by tempering the length field of the array-like structure. Well, our approach is to temper the start address of an array-like structure. Also, vector and ByteArray are not only candidates. There are other ActionScript objects hold array-like structure inside, and to prove this concept, I will start with the simplest array-like structure inside Flash, the string object. So if a class holds a string inside, a structure will be something like this. There will be a virtual function table, a reference count, and some other fields. Of course, there will be a string inside. And the string I'm talking about here is not the ActionScript string. It's not the class that's defined by ActionScript virtual machine. So some class, they try to just hold the string inside. They don't need so many operations. So they will use a very light-weighted self-defining string inside. So there will just be a buffer pointing to the content of the string and a length field. And if it is actually an ActionScript string here, there will be just an item reference pointer here. It won't be these 2 fields. So if a class holds the string inside, and somehow with the help of use of the free, we are able to release the class memory and occupy it with controlled content, where the start address of the string object can be any desired value. And right now, we can read the target memory through the string object. And after dealing with the target memory, let's say we can release this class memory again. I would show you how to finish this step in the real-world case, but for now, let's just assume we can release the memory again and occupy it with another controlled content. So the start address can be another value. And with such release and occupation over and over, the string object of this class becomes a read primitive. And that is the main idea of our exploitation method. Since there are many cycles of release and occupation, the method is named as use of the free. And maybe this is a very ideal situation. There's still one step before we're getting to this situation. Let's come back to the beginning of the use of the free. When the vulnerable object is released because of use of the free, it may not contain a string inside, so we should occupy with our selected class, which holds a string inside, and the same size of the vulnerable object. And because of isolated heap, these two class memory should also stay in the same heap partition. So after the occupation, when we invoke the virtual function of the downlink pointer, it is now the virtual function with the same offset, but in the selected class virtual function table being indexed. And the key point is that such type confused status isn't expected by any of these functions. So this unexpected behavior may help us release the class memory. And now we're in the rate primitive status we have discussed before. So here are the basic steps turning a use of the free into a rate primitive. I think it's enough with abstract concepts. Let's go through a real-world case. CV 2016-1097 is a use of the free I found in PSDK. PSDK is a class belongs to MediaCore package. The whole package is firstly introduced into Flash 19 beta, and I found this package by decompiling the player global file and cross-comparing it with its old version. The package contains many classes inside, but all of these classes is undocumented. Only some related information can be found from the prime time player SDK. It's another Adobe products. It's mainly used to develop a cross-platform TV-based application. And for the PC side, the SDK is mainly a bunch of ActionScript files. And my best guess is that the package I found here is a native implementation of this SDK inside Flash player, just to accelerate the running speed. Apparently, when first time this package is introduced into Flash, they haven't been thoroughly tested. I found many memory corruptions the first time they're introduced, and after reporting them to Adobe last August, they choose to remove the whole package from Flash player. So maybe for half a year later, when it comes to Flash 21, the whole package is brought back. And all the memory corruptions are reported fixed. But I found a new bug of PSDK that is the use of the free. So here are the code snippets to triggering the use of the free. The only way to get an instance of the PSDK is through a statical property, little PSDK. Apparently, this class is initialized and constructed by ActionScript virtual machine itself. So naturally, the memory should be destructed and cleaned by ActionScript virtual machine itself either. But the weird part is that it also contains a method called release, which can be invoked directly from ActionScript level to actually release the memory of PSDK. This is rarely the case for Adobe Flash. Normally, all the Flash objects should be completely managed by MMGC, the garbage collector. So the only way to release the class memory is you just don't use them. So the reference count will be 0, and the garbage collector will find a correct time, a correct moment to scan all the objects to see what to release and what to stay. But this class contains a release which, after invoking it, the memory of release will be freed explicitly. And as this class is undocumented, so we don't know if this operation is necessary or not. But the reference from the ActionScript level is still pointing to the class memory. So when we invoke the virtual function with this reference, there goes the old school book use of the free. And now that the vulnerability is well explained, let's go build the exploit. So first, we need to occupy the memory of PSDK after it is released. PSDK takes 32 bytes. There are 2 virtual function tables at the beginning part of this memory. All the member functions from the ActionScript level is indexed in the first virtual function table, and the destructor itself is indexed in the second one. And the destructor cannot be invoked directly. It is used by MMGC to clean the memory. And other fields are irrelevant to our exploit. So in order to occupy the memory of PSDK and manually check the classes under the MediaCore package, I think they are most likely the best candidates. classes under the same package, they are very likely to implement in a similar way, especially for the heap partition. So finally, I pick track. It contains 2 string fields and the same size of PSDK after memory alignment. So when PSDK is released, newly constructed track will occupy its memory. And right now, we will invoke the virtual function of PSDK. It is now the virtual function of track being indexed. Let's say we will invoke create dispatcher, which is located at the 14x offset of this PSDK. And it is now the virtual function of track located at the 14x offset being indexed. And this type confuse function call will treat the second double word of this class memory to be a reference count, decrement it, and release current memory if the reference count is 0. It is very like a destructor. The second double word of current class memory happen to be the length field of the first string inside the track. So simply initialize track with a single character string. Can we control this field to be 1? And after decrementation, the count will be 0, and then the memory of track will be released. So right now, we've got a downing pointer in type of track, but we still need to find a way to occupy the memory of track with our controlled content and then release the memory freely. And there is a very handy function called setByteArray, which I think is almost born to finish the task we have left. It can occupy the memory of track and release it at the same time. So setByteArray simply duplicate the input byte array inside metadata. And metadata is also a class under MediaCore package, so it is sharing the same heap partition with track and PSDK. And setByteArray will allocate a temporary space to pre-calculate the input bytes just to see its encoding and length, and then it will allocate a new buffer to storing the input byte array inside metadata. And since this temporary space is first allocated, if the input bytes is 32 bytes long, the same size of PSDK and track, then this temporary space is what occupies the memory of track. And what makes things better is that, as its name indicates, that this temporary space will be released automatically at the end of setByteArray. So what it means is that if you use setByteArray to occupy the memory of track, the class memory, is filling with controlled content but still being freed. So we can invoke setByteArray as many times as we need, and there will be no side effects to the free status to track memory. So recall from the last part, PSDK is released because of use of the free, and the newly constructed track would occupy its memory. And the type confuse function call will release the memory of track again. So right now we're in the read primitive status. And each time we want to read the target memory, we just use setByteArray to push a byte array inside the memory content of track. And where the 16 of that should be the start address, and the 16 of that happen to be the start address of the second string field inside track. So after setByteArray, the content of track is controlled, and when we invoke track.language, which is the second string field, we know the content of the target memory. And after that, we can read the target memory content by each character of this string object. And right now, I just set the length of the string field to be 4. There is no need to be a very large number, 8, 16, 1,000, since it is a string. When a string is returned to the ActionScript level, there is a encoding problem. So there might be some special character that broke your string. So for that case, you still need to read the content character after character. So we don't need to be a very large length, just use 4 will be okay. And that returning value can still be converted to be integer, and very easy to deal with. So right now we have got the ability to read any piece of the memory. I think there are many choices left for the next steps. Let's say we can read a stable location sprayed with vector object. Although we cannot crop the length field of the vector anymore, but vector is still a very useful method to heap spray. And all the vector object is filled with current class pointer, this. And when we read a stable location, we know that this pointer is located after the metadata of the vector object. And with this pointer, all the self-defined variables in the class can be located from the 54 hex offset, let's say the ByteArray and vector. And since we know the structure of this class, we know how to find the buffer inside. And with these buffers, we can use it to store shellcode, fake virtual function table, and rope chain, and all kinds of things. And this technique is firstly seen in hack team's Flash exploit. And it is very useful. It is make less brute force searching, so make the exploitation code more efficiency. And after all the buffers are filled and linked, setByteArray is invoked one more time to crop the second virtual function table of PSDK. And the reason we choose the second one instead of the first one is that it is the temporary space that occupies the memory of track, and there is a release of this temporary space. So there's one minor side effect. It modifies the first byte of current class memory during the released process. So we cannot fully control the first virtual function table, but that is not a real big problem. We just occupy the second one to be the rope chain. And the second one belongs to the structure. So after every line of our ActionScript code is executed, MMGC will kick in and find that the PSDK's reference count is 0, then it will try to clean the memory of PSDK. That is the moment our rope chain is executed. The rope chain is simply pointing EAX to a controllable memory, whether EAX -8 and EAX -4 to be the start address and the length of the shellcode memory, and then we invoke the wrapper. The wrapper itself will call virtual protect to set the executed bit of shellcode. This wrapper code is firstly used maybe 2 years before, but the searching pattern for this wrapper hasn't changed. You just point EAX to a controllable memory and then call the wrapper, then everything goes smooth. The executed bit of the shellcode will be set. But the searching pattern hasn't changed until Flash 22. The changing for the search pattern is from EX -8, EX -4 to EX -C and EX -8. And the changing for that is that memory protector, a new mitigation, is added into Flash this June for Flash 22. Although it doesn't affect our exploitation or the bug or the searching or the wrapper, the functionality of this wrapper, but it do add extra fields to some kind of functions inside Flash. And I will discuss the memory protector for the conclusion part. And then after the wrapper is invoked, the executed bit is set for the shellcode, and then we jump over. So as a demo, the exploit is running under Windows 7. The only part will be time-consuming is the read primitive part. As you can remember, there will be 6 or 7 lines for the read primitive to work, and this is more heavyweight compared to ByteArray or vector with just an index number. So currently, what we have discussed is all under 32-bit environment. So what about a 64-bit environment? First, the pointer is changing from 4 bytes to 8 bytes. And so many class size is different. And as a result, PSDK and track are not in the same size. So they cannot occupy each other. So we need to pick another class, and that is media resource, which is also under MediaCore package. And it is now the same size of PSDK. So after PSDK is released this time, we initialize a media resource class that will occupy the memory of PSDK, as media resource also contains a string field. And after that, we still use a type confuse function call to release the memory of media resource. And this type confused function call will treat the F0 hex offset to be the reference count, decrement it and release current memory if the count is 0. So this is very like 32-bit, but unlike 32-bit, it is not the 4 hex offset, it is the F0 hex offset. And we cannot control this part of memory with MIDI resource itself anymore, since MIDI resource is only 30 or 40 bytes long, it cannot cover the F0 hex offset. So we need to occupy this part of memory before PSDK is actually released. That is not difficult for us, and we just need to invoke setByteArray one time before PSDK is actually released. And there are two reasons. We can just invoke one time to occupy the part of memory. The first reason is that the memory location for PSDK and track and MIDI resource, they're different locations compared to traditional Flash objects. Traditional Flash objects are managed by MMGC where virtual alloc on a self-defined Flash heap. But PSDK and track and MIDI resource and auto class and the MediaCore package, they're managed by malloc and free directly on the default heap or the CRT heap. So meaning that the memory of PSDK is rather pure. So after the initialization of PSDK, there won't be any interference during our exploitation process. The memory after PSDK won't be allocated into our setByteArray. So when setByteArray is invoked, it is the first time the memory after PSDK is allocated. So the memory of PSDK and the temporary space allocated by setByteArray and actually buffer stored in metadata. And these three pieces of memory, considering the memory alignment, will help us to occupy the memory located at the F0 hex offset to be 1. And after that, when we invoke the type confuse function call, the memory of MIDI resource will be released, just like before. But we cannot read a stable location for 64-bit environment. There's all the traditional Flash objects heap spray is high 32-bit randomized. So even if you have sprayed terabytes of memory, you cannot control a stable location with controllable data. Luckily, I find that spraying malloc the Flash objects and the Windows 7 doesn't derive the high entropy of heap randomization, meaning that the high 32-bit is still 0. So I just need to pick another class under MIDI resource. I choose add-asset, which works very similar to array. You can store different class objects inside. And when you initialize this class, many times the class inside will duplicate themselves to spray the memory. And after that, during the brute force search for the sprayed memory, we can find a flag. This flag belongs to MIDI resource. It is also one of the class that is being sprayed, and it contains an integer value. It can be used as a flag. So when we find that flag here, we know the MIDI resource is located right after flag, and metadata is next to MIDI resource. The metadata can be used as a replacement of ByteArray or vector to store controllable buffer. As we have discussed, setByteArray can put a controllable memory inside metadata with. So we can find this buffer where fixed offset for each step. setByteArray store the input bytes with a hash map structure. So the second step is the offset for the second step is calculated via a hash function. So if the hash value is calculated with the key names that we used, or that is the input parameter of setByteArray. So we don't want a hash collision. The hash value can only be 0 to 7. So it is very likely to be a hash collision, but we don't want a collision. If that happens, there will be a list structure inside metadata that will make things more complicated to find this buffer. So as we don't need so many buffers, we just need to pick different key names, and so that they will be stored in different buffers. We can find them where just fix offset. And with these buffers we can use them to store the shellcode, the rope chain, and all kinds of things. And fake root function table trick works like just before. So that is 64-bit environment. And currently, all the experiments are conducted under Windows 7. So what about Windows 10? First, I didn't intend to build a fully workable exploit under Windows 10. As building the exploit under Windows 7, there are so many new things. New class, new heap spree method, and so many reverse engineering made me exhausted. So for Windows 10, I just need to take a quick peek to see what's the difference. And PSDK is first still allocated by malloc on the low fragment heap. And this is the same as Windows 7. But low fragment heap itself is changing from Windows 7 to Windows 10. There is a randomization adding into this heap, meaning that for Windows 7, when the memory block is released and it comes down to the free list, at the end of the free list. And when next allocation is coming, the memory block at the end of the free list will be the next one to be allocated. So the free list itself works very similar like a stack, last in, first out. It's very predictable. But for Windows 10, the things is different. When the memory block is freed, it comes down to the free list. But when next, let's say there are 16 blocks in this free list. But when next allocation is coming, low fragment heap will randomly choose one of the 16 blocks inside free list to be the next one being allocated. So from the use of the free aspect, we don't know if our class memory is occupied or not with just one allocation after the use of the free. So a simple idea to bypass this randomization is that you have said there are 16 blocks in this free list, so why not we just allocate 16 times to make sure the memory of the freed object is occupied. But that is only partially correct. So after 15 allocation, there's everything goes okay, but for the 16 allocation, it won't be the last memory block in this free list to be allocated. Low fragment heap will allocate a new free list with memory block inside, and then randomly choose one of those to be the next one allocated, just to enlarge the randomization. But this randomization is still limited. So after maybe 2 or 3 cycles of free list allocation, low fragment heap will finally remember, well, I still have a memory block in the first free list, so why not using it? Then it will allocate the last memory block inside the first free list to be the next one to give you. And that is the moment we can occupy the memory of our freed object. These demonstrations are all just observations of my experiment. It is not a fully reverse engineering of NTDL to see how low fragment heap works. But it do work for my exploitation. So after PSDK is released, we can construct the track hundreds of times, and it will make sure the memory of PSDK is occupied. And after that, we still use a type confuse function call to release the memory of track this time. And this type confuse function call actually makes things easier compared to Windows 7. We don't need to control any part of the memory. Just make sure the input parameter to be 1, and the memory of the track will be released. And after that, we're in the ready primitive status as before. But I didn't go any steps further. For the next step, we still use setByteArray, but it also need to be multiple occupation. So you need to invoke setByteArray many times to occupy the memory of track and then read any address. So although Windows 10 brings us a tough environment, I think use after free, this method can still find its way to read primitive. I think I'm talking a little faster. So for the conclusion, first about the fix of this bug. After reporting this bug to Adobe, they choose to manually remove the reference, which is used to invoke release. And I said manually here, meaning that this fix can be bypassed. So I bypassed this fix by declaring 2 references to PSDK and invoke release with one of them, but triggering the use of the free with another. So there goes another bug, CV 2016-4248. And when I try to exploit the second bug, it is now Flash 22. And as we have discussed, memory protector, a new mitigation, is introduced into Flash. This new mitigation is used to delay the free of objects. So maybe something learned from Microsoft, but it doesn't affect our exploitation or the method or the bug, everything we have discussed. And the reason for that may be memory protector only focus on MMGC protected objects. It doesn't affect our malloc or freed objects. So for the second fix, maybe this is a new trend for Adobe, moving all those traditional objects to default heap. And I think newly introduced classes for Adobe these days are now all using the default heap. So they can derive the mitigations brought by Microsoft. Meaning that now if you want to exploit Adobe Flash, you need to bypass not just Flash heap mitigation, also the Microsoft heap mitigation. So for the second bug, I choose to manually, they choose to this time fix the bug, they choose to remove the release function. So if they don't need this function at all, why should they introduce it at the first time? Maybe this is just a temp fix for them. So Adobe also fix bug with temp fix and actual fix. Sometimes I have met such temp fix 2 times before, and the first time is a heap overflow. So I've got a heap overflow, but after a fix, I find the heap overflow not working anymore. And the reason for that is the heap memory is doubled. So for my heap overflow, I cannot overflow that much of memory. Meaning that the heap overflow is fixed, I think, for that time. But after several versions of Adobe Flash, and I find that the heap overflow is back. And the reason for that is the calculation of the heap size is rolling back to its old version. And I think the reason is that for the first fix, Adobe is not trying to fix my bug. It is trying to fix some other's bug. And they don't know how to calculate the right size of the heap, so they just use a temp fix, just enlarge the heap size to be a very large number. And after several cycles, they know how to fix the bug, so they just use the old calculation. And although the original bug of other people's is fixed, but for my bug, it still exists. And the second time is for the PSDK thing I have just discussed, the MediaCore package. When I first reported the memory corruptions to them, they choose to remove the whole package. And the first time, I think maybe they shouldn't made this class public. They should just use them internal. And when they're rolling them back, I think it's just a temp fix. As there are so many memory corruptions, they may need time to actually fix all of them. And for this removing of release, maybe it's just a temp fix. So after several versions of Flash, the release, if it is still come back, but with just manually remove of the reference, it may still contain a bypass of the fix. And for the use of the free method, I think it's a relatively common way to exploit use of the freeze in Adobe Flash. Although the first steps seems a little complicated and contains many reverse engineering. But I have accomplished such tasks in the 3 different versions of Flash, 32-bit and 64-bit, and Windows 7, and 32-bit, and Windows 10. So I think it can still work for other use of the freeze. And right now, we're dealing with a string structure, and thus give us a read primitive. And in the future, we may find other class hosts, other structures that can be corrupt, so that give us a write primitive. And the problem with string is that when you try to read the content of the string, everything is okay. But when you try to write the string with the target address you pointed, it doesn't work. It will allocate a new memory to store the content you want to write, and then return that pointer inside the class. So we cannot just write any part of the memory. But if you can find another structure that is more like an array, meaning that when you try to write the memory, it is still the pointer inside the structure to be the memory you're going to write, then a write primitive. That will be much helpful to bypass the mitigations for Windows 10. An idea behind the use of the free, I think, is more common. I've heard that for the last, maybe not the latest one, the one before the latest one, iOS jailbreak, they're using a very similar way to exploit a kernel bug. They will use several cycles of release and occupation of a use of the free, and thus have introduced type confusion. And I think the idea behind these two bugs is very similar. So use of the free, I think maybe they can implement in different softwares and different platforms. And I think maybe that's all for my presentation. Thank you.